Hello, everyone, and welcome to the next Math Talk episode. Today I'm joined by Dr. Emily Riehl, who's a professor at Johns Hopkins University, author of several books on category theory, including infinity categories, as well as, well, some of you might recognize her as an expositor of mathematics. She's no stranger to articles online and YouTube, as well as one of, if not the founding member of Spectra.
Certainly not
founding member, which is an organization that supports LGBTQ plus mathematicians. So welcome.
Thank you.
And do you maybe just want to start off by saying a few words about your current research interests?
Okay, sure. So I fell in love with category theory in a kind of gap year master's program between completing my undergrad and starting my PhD. I went to Cambridge for a year and took this course and was immediately enamored of the proof techniques. It felt like a style of argument that really appealed to me. And within category theory, I was most interested in the categorical structures related to abstract homotopy theory. So traditionally, this is a formalism introduced by Daniel Quillen called model categories, and my thesis was related to something like that. Nowadays, we understand model category as a presentation of an infinity one category. So that's a weak infinite dimensional analog of an ordinary category. And so my interests kind of evolved in that direction. But I guess in parallel, one of the components of a model structure that particularly interested me and was related to my thesis was being used to understand the semantics of homotopy type theory, which is this new kind of experimental, certainly still under development, alternative foundation for mathematics. So I got pulled in that direction as well. And there's lots of connections between homotopy type theory and higher category theory, which we could talk about in more detail. And so now I guess I describe my research as sort of split between those two areas. So abstract homotopy theory, principally in the guise of these weak infinite dimensional categories, but also homotopy type theory.
Cool.
Yeah.
So before we dive in to all of that goodness, I normally like to start off by taking things all the way back.
Okay.
And asking you how you first got interested in mathematics. Like, when did you even recognize that math was a thing, and what was sort of that journey of your first discovery that you enjoyed it?
Sure. I think I may be a bit unusual in that I've loved math my whole life, as far as I can remember. I was interested in, patterns in the calendar when I was a kid. My elementary school library had all these wonderful math books. There's the sort of I Hate Mathematics and Math for Smarty Pants series, the Sideways Arithmetic from Wayside School. I devoured all of those. I had a lot of really good math teachers at all levels who would give me little worksheets to do. My fifth grade teacher gave me a worksheet on base 4 arithmetic, for instance. So there's always sort of these little, for me, it felt like play excursions that kind of piqued my interest and gave me a glimpse of sort of what real mathematics was. And I think I kind of fully committed to, at least majoring in mathematics and then being a mathematician in sort of early high school when I was first exposed to proof. And that world of kind of creative mathematics, expository mathematics really appealed to me. And so here I am.
And then, so you said that you discovered category theory between your
undergrad and grad school.
So maybe can you say a bit about like how that came about, or like in undergrad, did you have particular tastes at that point in time? Were you just sort of devouring everything, or?
Sure. Yeah. I mean, so despite being certain from an early age that I wanted to go to grad school in mathematics, I wasn't one of those undergraduates who are already grad students, in a sense, if that makes sense. So I was an undergrad in the US, so with a kind of liberal arts education system, and I decided my strategy was I was going to take, hard math courses and make sure I was well prepared for grad school, but this was my opportunity to like live out the liberal arts dream. So I took a couple courses in queer theory. I took an American intellectual history course that was wonderful. I took a year-long music theory course. So that's kind of where I was as an undergrad. I was still taking, maybe 2 math courses a semester, but I wasn't really doing research. I wasn't going sort of that far beyond the undergraduate curriculum. I mean, I was in a great math department, so the sort of standard curriculum was sufficient. But anyway, so as an undergrad, my taste kind of ran more towards algebra than analysis. I wrote an expository senior thesis on algebraic number theory and Leuventate formal groups, local class field theory.
Oh, cool.
And I thought that was great. And if there was a problem like that in algebraic number theory, I might have continued in that path. But I don't know. Then I got seduced by category theory and
right.
went over to the dark side.
Fantastic.
Yeah.
So side note on the music theory. So you're in a band. You play bass in a band.
So I was in a band in my postdoc, and then I moved. I think
okay.
I still get to play with them occasionally. So they're called Unstraight. They're based in Boston. Haven't been super active since the pandemic, but anyway, I was the original bassist and occasional guest bassist, I guess.
Cool.
Whenever
Cool.
I'm in town. Yeah.
I was wondering though, since so you've taken some music theory, so maybe you like to nerd out on it. Do you know of this book? There's a book called The Topos of Music Theory.
No, I don't. Who wrote that?
I don't remember the authors. I think they're more. Actually, I don't remember. Yeah, even the authors' names. I have a PDF on somewhere on my computer. The last time I looked at it, my topos theory was not strong enough.
Okay.
And it's a tome, like it's hundreds of pages.
Okay.
But I was curious if you knew about it, and if not, just let you know that this thing exists, because someone tried to formalize music theory using topos theory, and it's I'd love to understand it at some point.
Great. Well, that's a great tip. I'll have to check it out.
Yeah. So your when you discovered like category theory in your gap year, was that you were just looking around, or did this come from like a conversation with someone? Or...
Well, so gap year is maybe a little strong. I went to Cambridge and did part 3 of their master's program.
Oh,
it's a very different experience attending this master's program as a student, from the US who's deferring a PhD there, because it's sort of a low stress, opportunity to explore, take a lot of courses. But yeah, and I mean, I had a great time. So, the way the system works is they have like, I don't know, several dozen courses on offer every term, and one of them the first term was a category theory course. So my experience of it, I think like most students, is it was completely mystifying. I mean, the lecturer was Peter Johnstone, who's very clear, very careful. He presented a beautiful course that went a little bit over my head, but I had excellent notes. And the way the system works in Cambridge is you sort of attend lectures for 8 weeks, and maybe there's a few problem sets in that period, but it's not nearly as emphasized as it is in the US. And then so this was from October to December, and then in June the following year, there's an exam. And so there's a period of a few months before the June exams where you dig out your notes from the fall and go back over everything. And part of the expectation is that you would be able to reproduce any proof that was given in that course, which seemed very daunting, but was a wonderful way to internalize this material. And
right.
So I feel like I was exposed to it first in the fall. I understood it first in the spring, and then and then I went to grad school and took my gen ed courses and other things, and so I sort of let it marinate for a year before coming back to category theory, really.
And then so you got hooked on category theory. And well, I guess what were your sort of first explorations in category theory, like early career working as a category theorist? Like, did you go straight to infinity categories or?
No, and I definitely don't recommend. So that's a great question. I'm glad you asked. I definitely don't recommend that.
Okay.
So I was a first year PhD student at Chicago, which is, very intensive course sequence, lots of homework, exams and all of that. So that's all I did for a year, did not attend seminars, did not attend talks. I mean, this was pre-Zoom, so there weren't all these online seminars or things like that.
Right.
Didn't attend conferences. At the end of that period, then all of a sudden my schedule opened up and I was free to do whatever. And actually what I did is I took out McLean's categories for a working mathematician and read it cover to cover and did all the exercises.
Oh, wow.
I guess that sort of has always been my style, to be a little more thorough and not skip over things, even though I sort of quote unquote know them already. And I'm really, really glad I did that. I was carrying that book around at the International Category Theory Conference that summer and a little bit embarrassed by that. But there's a lot of really good material in there that I hadn't been exposed to, sort of ends and coends, con extensions, things like that. And I feel like, sort of that humility maybe in that discipline really served me well as providing a foundation to build on a bit later.
Right. And to what extent, like, so you decided to eventually write your own books on category theory. So what sort of, I mean, of course, we all love writing mathematics, but is there some sort of like, was there a specific need that you saw for like a new category theory text, or and related to that, to what extent maybe did that text impact choices or in your first book?
Right.
Or any of them?
Sure. So my first book was kind of an accident. So my first book is something called Categorical Homotopia Theory that came out of lecture notes from a graduate topics course that I taught during the first year of my postdoc. And I sort of put enough work into the lecture notes that they were sort of book length by the end. And anyway, so that's what happened there. But the category theory book was deliberate. I also wrote it as lecture notes for a course that I taught, but I pitched the course because I wanted to have an opportunity to write this book. And the motivation is something that I think is a kind of very common experience of category theorists when interacting with other mathematicians. You'll meet somebody, in this case, I have a particular memory in mind that this was a graduate student, so a few years young, somebody who was a few years younger than me, who's, very confidently saying, there are no theorems in category theory. There's sort of no content in category theory. And, my instinctual reaction is like, you just don't know enough category theory to know any of the theorems. But I think part of what creates that impression is, category theorists value the definitions they make often more than the theorems. And I do think that sort of weighting is the correct one. In general, it's very easy to make an abstract mathematical definition. I mean, you could, throw together a bunch of sets, throw together a bunch of functions between them, throw together a bunch of axioms between those. Now you have give it a catchy name. Now you've got your new mathematical definition, and you can start proving theorems about it. So how do we evaluate and how do we compare these definitions? It's kind of a rich question. There's sort of two tests. Number one is there should be examples, and number two, the examples should be illuminated by the abstraction somehow. So, a group is a very historically successful definition because there are a whole lot of examples, and what's going on in those examples is somehow clarified by thinking about them as groups as opposed to just as collections of symmetries or whatever that means. So a lot of category theory is these new abstract definitions that just explain what sort of structures mathematicians had been working with previously in some particular setting.
Mm.
And for the best ones, they clarify it. So so from that perspective, a lot of the contribution that category theory makes to mathematics is just in stating these definitions rather than proving the theorems. Often the theorems are quite easy to prove from the definitions if they're well chosen. So anyway, the goal of this book was, I guess, really to explain to a mathematician, a beginning grad student in any field, advanced undergraduate who's thinking they might go into graduate school in mathematics, sort of what category theory is for. So, the title is Category Theory in Context. The aim is to sort of illustrate the kind of core theorems in category theory, right adjoints, preserved limits, for instance, by as many kind of concrete, which is a joke because of course it's all abstract mathematics,
Right.
But by as many applications as possible. There is also an epilogue that was written to this graduate student called Theorems in Category Theory, which is like literally just a list. But anyway, that was the motivation. So.
Yeah, I do think I've certainly come across people who undervalue category theory and have made these same sort of comments like, oh, it's trivial, there's no theorems. But I do think even outside of category theory, the art of definition is really important,
Sure.
So
yeah, not at all unique to that field. I agree.
Yeah, like in I would even in my own field in the Langlands program, there's people are trying to make it because the original thing is basically like, oh, there's a surjective map. Well, who cares about surjective maps? That's that we want a functor. That's a real meaningful connection, right? And so now there's sort of a push. People are trying to grasp for the right definition that somehow makes this a more categorical statement because it's somehow more meaningful. And I think this is also really important in the proof assistant community as well, because you have all these equivalent definitions, but it sort of sets the tone for how you're going to do all your proofs, which one you pick to be the definition of some object, right? So yeah. So then how did you start getting into, so I mean, it's very easy for me to imagine you're doing infinity categories, you hear something about homotopy type theory, which it's like, hey, our types are infinity groupoids, and it's like, wow, that sounds perfect. But is there more to that journey about how you specifically came to homotopy type theory?
Right. I mean, there's kind of a social, oh, thank you.
Yeah.
There's a sociological aspect to the story, I suppose. So, I mean, part of it was, kind of being in the right place at the right time. So, so homotopy type theory is based on this system of dependent type theory, particularly in a presentation by Per Martin Luff that was developed initially in the 1970s as a foundation for intuitionistic mathematics. There was, I guess, so a key component in this formal system is the treatment of the equality relation. So in traditional foundations, equality is axiomatized as a binary relation that is reflexive and satisfies something called indiscernibility of identicals. In this formal system, equality is a type and it's called identity rather than equality. So we have these identity types, and there are different ways to express the rules for identity types. So Per Martin Luff had this really ingenious idea that there's some analogy between identity types and the natural numbers, and that they're both inductive somehow. They're both freely generated by something. In the case of the identity types, this is the reflexivity terms. But the specific choice that I'm trying to talk about is something called intentional identity versus extensional identity. So extensional identity means that if X equals Y, there's at most one proof of that. And intentional identity suggests or admits the possibility that there might be multiple proofs. So it doesn't require that any two proofs that X equals Y are themselves equal in the sense of these identity types. So it's that intentional perspective on identity type that admits a higher dimensional interpretation of this entire formal system, and that was sort of first observed in the mid 1990s. Hoffman and Stryker come up with a groupoid model of dependent type theory with intentional identity types, where the types are interpreted as groupoids, and the terms and the types are objects in the groupoids, and a proof of identity or an identification between them could be an isomorphism in that groupoid. And in particular, you could have multiple isomorphisms between the same objects. And so that's this idea that you might have multiple proofs identifying two different things. And so then that, about 10 years later, through sort of joint independent developments of Wojcicki and Aude Warren, led to this sort of homotopy theoretic interpretation, where now we're thinking about types not just as these one-dimensional groupoids, but perhaps infinite dimensional homotopy types. So a groupoid is like a one type, and then there's also two types and three types and things that don't have a truncation level. So this was these ideas were crystallizing in the mid-aughts, and maybe in something like the modern form by the kind of late aughts. I was a PhD student at that time at Chicago. Mike Schulman was also there, so there were one of the kind of key early figures was an academic sibling of mine, and then the sort of decade later, when I was a postdoc, there were various conferences in homotopy type theory, and I started getting invited to them. So the sociological reason is I'm suspicious that my gender had something to do with the fact that I was getting invited to these conferences. There weren't a lot of women in the field, and in particular, if you want to have a female speaker, you might invite somebody in an adjacent field to come to your conference. And so that happened to me on a few occasions, but it was a wonderful opportunity to come give an unrelated talk at a homotopy type theory conference and then learn some homotopy type theory. And so over a period of maybe 4 or 5 years, I was kind of recruited into the field as by some of the folks who were in it. So
Excellent.
Yeah.
Excellent.
Yeah.
Yeah. One of the things I love most in mathematics is analogies. And there's these wild analogies between fields that lead people to arguments, and it's still so magical to me, the different interpretations in homotopy type theory. Like, I remember when I was doing some reading for this summer school I went to, a number of us were reading together, and we were trying to prove something, and one person was thinking about it geometrically as if it was like a fibration, and one person was thinking about it just as a statement about propositional logic, and they both came to the same proof through their own interpretations, and it's just something magic.
It does feel like magic, I would say. So
Yeah.
I mean, particularly when you're talking to these computer scientists who somehow could come up with these sophisticated original arguments that are new proofs of classical theorems and homotopy theory and algebraic topology. I mean, it's really astounding. So
yeah, it's interesting to think that you could hand a bunch of these statements to a logician, tell them to interpret everything in terms of logic. They come back with some theorems, and you go, oh wait, if we interpret that homotopically, oh wow, I wouldn't have expected this thing. Yeah. So have you done a lot with proof assistance as well, or are you more just on the sort of theoretical side of homotopy type theory?
Yeah, sure. So one of the advantages of this formal system, or really any formal system that's kind of based on type theory, dependent type theory, is that it's you're already sort of speaking the language that computers speak. So one of the reasons that Wojcicki, one of the founders, started learning about type theory is he was interested in formalizing his research mathematics, and felt that maybe set theory wasn't the optimal language with it to be interacting with a computer. So So homotopy type theory being based on dependent type theory is very amenable to computer formalization. So far, I've engaged with formalization mostly as kind of an expository device. So in particular, I taught a topics course in homotopy type theory, I guess a year and a half ago now at Johns Hopkins, following a wonderful new book by Egbert Rocha, which is in press, also on the archive. So it's out now. It's called Introduction to Homotopy Type Theory. This is definitely my recommendation if you want to learn homotopy type theory. And one of the things that's so wonderful about it is he's formalized the entire thing in AGDA. And so that made me feel confident that I could write all my problem sets in AGDA, even though I was sort of teaching myself along the way. So AGDA is a kind of bare bones to some extent computer proof assistant in that essentially what you're, as a user, you would state a theorem that you intend to prove by writing down the name of the type that encodes the statement. And then to prove the theorem, you need to write down the name of a term that inhabits that type. And in AGDA, you essentially just write down the name of the term. It doesn't have a lot of tactics or widgets or whatever. You're essentially just kind of working directly in the type theory. But it's a wonderful learning tool because I think we've all had the experience of sort of sketching out something on paper. Maybe an idea comes through in your head and you think it's probably right, but you're not 100% sure that every single step is correct. And that's what the proof assistant can provide for you is, when I was, preparing for class, sometimes I would check an argument I wanted to give by writing it in the proof assistant. And, a thing that I discovered that way is a lot of times I was inducting over something, particularly over sigma types. I kept forgetting that I was inducting over sigma types. And, I didn't realize that I had used an induction step in my proof somehow. And then that sort of changes whether, the conclusion is sort of up to, propositional equality or up to judgmental equality. And I caught a lot of small issues like that. In this proof assistant, I found it really clarified my thinking, it improved my teaching. And so then what I did for my students is I would write problem sets to accompany for each week in the course, some of which was essentially to just formalize something we had discussed in class. So if there was a particularly important construction or proof, I would ask them to give us a formal version of that. And I think it just really helps a lot with learning, particularly if you're trying to learn on your own or in the absence of a community. Because of that experience, I'm sort of most comfortable in AGDA than any other proof assistant. But I have experimented a little bit with COC, which has tactics and has the sort of proof mode where they list the assumptions up top and the goals on the bottom, and that's kind of fun to interact with. I think that's better for a student at a different level, maybe an undergraduate who is learning logic for the first time and will have a little bit of trouble keeping track in their head exactly where they are in the middle of a logical argument. So a proof assistant like that would be more amenable. I've also played the natural numbers game, which is an introduction to Lean. The homotopy type theorists are unfortunately unable to formalize their mathematics in the current version of Lean because of something sort of deep in the engine of the proof assistant that forces you to use extensional identity types as opposed to intentional identity types. So for that reason, I haven't really engaged with Lean further, but so I'm an amateur user, I guess.
I'm on the point of it being useful for learning on your own. This was a point that Kevin Buzzard made in a talk was, so when he was first experimenting teaching a course using Lean, is one of the real values is that you get live feedback, right? Normally you hand in an assignment, you wait for someone to grade it over the weekend, you have no idea how you did until afterwards. But when you're trying to write a proof in a proof assistant, the code compiles or it doesn't. You know immediately whether your proof is working or not, which I think is really valuable. And that makes me excited, like as I, once I move on to a postdoc or professor position, I'd really love to experiment teaching a course with a proof assistant and leaning on it as a pedagogical device.
Yes, I'm very optimistic about this. So in the Intro to Proofs course, the undergraduate Intro to Proofs course at Johns Hopkins, when I teach it, we spend a week doing using COC, and it's really just about I don't know, this connection, I guess, between intuitionistic reasoning and maybe proofs of implication are functions where you just sort of define the function. So we in my version of the course, we just do a little bit of exposure to those ideas, and the students have an opportunity to do one of their problem sets in a proof assistant. There are people who are a lot braver than I am who will teach an entire version of an Intro to Proofs course using a proof assistant. So Sina Hazratpour, who's a postdoc at Johns Hopkins right now, taught Intro to Proofs this past year entirely in Lean, and very ambitiously in Lean. They were formalizing the innate lemma by the end somehow.
Wow.
What I'm optimistic, I don't, in my view, I guess, as somebody who's not as adept with computers, maybe, or doesn't really have a programming background. I think there is still a barrier in learning to use a computer proof assistant now. I mean, you're learning the sort of the syntax, the language, the conventions of paper proofs, let blah blah blah.
Right.
Without loss of generality, we assume, there's all these, things that a student has to learn. Right now the experience of using a computer proof assistant is you have to then learn an additional, syntax or language about, introductions, exact, apply, all these tactics that are used in the proof assistant. So what I'm optimistic is that within maybe a decade, there'll be a sort of a more natural language way to interact with one of these computer proof assistants where you could write, let so-and-so be whatever. The computer will know that what you meant to do is you're introducing the variable in whatever type is the hypothesis. It'll update the goals and the givens for you, which I think that interactive element is the real advantage of the computer system. And when that happens, I think all Intro to Proofs course should be taught this way for exactly the reason that you intuited, which is that the real-time feedback is so valuable, and it's much better to know that your argument is wrong immediately than like 2 weeks later when you turned it in and the TA gets it back to you.
Right. Yeah, and I think my sort of dream for the future is that eventually it is basically like you said, like I essentially imagine that in the future it'll just be like writing in LaTeX, and it'll be about as easy. And I also think too that could really help things in, say, the refereeing process, right? Because if your code compiles, I think there's still a need for refereeing because you want to add some exposition in there, and just because you formalized some symbols and proved it is like, okay, do those symbols really mean that thing? And there should be some oversight, but I think that will also be a great boon to mathematical progress.
Yeah, I agree. I'll reiterate some of the caveats that you mentioned just there. There is always a question after you formalize something, it compiles. That certainly gives you some sort of information, but it doesn't necessarily tell you that you've proven the theorem you intended to prove. So Johan Kamelin has given a talk where he describes, after the completion of the liquid tensor experiment, the sort of examples that they developed with the aim of, convincing a user that what they formalized is actually, that problem and not something else.
Right.
So, I think he calls it abductive reasoning. So if it looks like a duck and it quacks like a duck, then it's a duck, something like that.
Right.
So I think that aspect of interpreting computer formalizations is maybe a little under theorized now, and it'd be interesting. But a thing that I like about them is there's always this tension in mathematical writing between the right level of detail. So,
Mm.
we've all read things which do not have enough details, and have absolutely no idea what the proof means or what proof is in mind. Maybe the proof isn't even there.
Mhm.
But then I think there's also a possibility of having too much detail. I mean, sometimes when I'm writing something, I feel like, it's really going to be easier for the reader to figure out this step for themselves than for them to figure out what it is I'm trying to say here.
Right.
And and of course, readers are not a monolith. Everybody has their own
Mhm.
individual tastes, and so the level that's appropriate to some reader would be different for some other reader, be different to some other reader. Much less if we're trying to optimize for readers coming from different mathematical communities and so on and so forth. So one of the things that I've, as an editor, I've handled a couple papers in homotopy type theory, some of which come with computer formalizations. And what's wonderful about that is it really kind of hits both marks quite well. So, the computer formalization necessarily is sort of full details.
Mm.
You can't sort of skip a step in a formalization. And then that allows the paper to be sort of much shorter. So induction in dependent type theory is a more general technique than just induction over the natural numbers, but it's essentially like that. And in this paper that I handled, there are a lot of proofs that in the paper version it would just say by induction, and it very succinctly gives you the idea.
Mm.
And if you want to see exactly, did we first induct over this and then induct over this, or the other way around, or does it matter? I mean, there is the formalization on GitHub, and
Right.
yeah,
Right.
So
Yeah, I think that certainly can make papers a lot easier to read if there's big proofs that last 3 pages and it's like, okay, I don't really need to scroll through this. I need the ideas, and then okay, maybe I'll dive into these proof techniques later. Yeah, certainly.
yeah, totally agree.
So one question I normally like to add. Well, typically this comes towards the end. I'm not sure how much more time we have, but I'll just ask it now. So I got the impression from your recent video on Wired that your philosophical stance is more Platonistic of mathematics. So would you describe yourself as a Platonist or like a purely formalist, or where do you land on that?
Yeah, so what exactly do you mean by formalist?
Well, I mean, so well, I'm actually not sure of the proper terminology, so I'm probably butchered. There's probably someone who does mathematical philosophy who's cringing as they listen to this right now. But sort of as opposed to the Platonist who believes that maybe math is truly out there, and there's maybe an objective. The continuum hypothesis is definitely true or definitely false, and whereas the formalist says, well, it's all just a language. Math is purely our own construction, and it's not really out there.
Great. Yeah, I mean it's a rich question, frankly. So I mean, there's definitely something Platonistic in my worldview, which is that I do believe mathematical objects have some sort of existence. That's clearly not an existence in the real world, or in the maybe the sense that we're used to other objects existing, but I still think is real. So this video is a expository video on infinity, and at one stage I'm talking with Adriana Salerno, who's a fellow mathematician, about whether infinity exists, because it's quite there's infinite sets, of course, all over mathematics, but it's hard to find an infinite collection of things in the real world. And my argument for why I think infinity exists is that she and I are two different people, and I think we have a lot of the same ideas about what infinity is, and that seems to me as evidence that there's something that we're sharing in common. On the other hand, I feel like I'm a bit of a relativist when it comes to I don't know, foundation systems, or when it comes to something like the continuum hypothesis, which is independent of some axioms of mathematics, but resolved in other axioms of mathematics. So this point of view comes, so if you're a category theorist, at some point you learn about these things called toposes. Maybe I'll just refer to one topos, I guess, like this topos of music.
Of music, yeah.
So what a topos is it's a category, an ordinary category, a one category that has a lot of the structure like the category of sets. And each topos has its internal logic as a way to interpret, sentences, constructions, and set theory is telling you some information about the topos. And a thing that's, so some toposes satisfy the axiom of choice and other toposes violate the axiom of choice. So a categorical way to state the axiom of choice is that any surjective map has a section. So a surjective map from a set A to a set I gives a partitioning of A, of the domain, as a I indexed family of sets. I was the codomain. So for each element downstairs, the inverse image, the fiber, is the set indexed by that element. So to say that that map is surjective says that each element downstairs, each index I has a preimage. So each of these sets, A sub I, is inhabited. And then a section would be a simultaneous choice for all indices I of an element in the set AI. So that's what's permitted. The data of that section is what the axiom of choice gives you. So for certain toposes, all epimorphisms have a section. For other toposes, they just don't. And so, from that point of view, it's not as if the axiom, it relieves you from the pressure of trying to decide whether the axiom of choice is true or false.
Right.
It's true in some settings, it's false in other settings.
Right.
So I don't know if Platonism requires you to have one worldview. I guess I have sort of a mini worlds sort of worldview. So that's right. So one part of my philosophy is that these mathematical objects exist. Another part of my personal philosophy is this sort of many worlds point of view on foundations. And I guess a final part of philosophy is I tend to have a more structuralist point of view on, kind of what a mathematical object is than maybe I don't know what the opposite of structuralism, if somebody can fill that in. But what I mean by that is, the definition of the natural numbers that appeals to me is one, via Dedekind's categoricity theorem, which is that if you have a set with an element and an endomorphism that satisfies the piano axioms, then it is isomorphic to the natural numbers. So as a category theorist, anything that characterizes an object up to canonical isomorphism is a definition, and in fact is maybe the definition. So the natural numbers to me sort of spring into existence from the piano postulates, not from some particular construction of the set of natural numbers, like the von Neumann construction or the Zermelo construction of the finite ordinals. So anyway, that's all I'll say about philosophy.
Okay. Well, an important point came up there. So you're in the toposes camp, not the topoi camp. Or do you have some people have strong feelings about
I do not have strong feelings about that. So,
okay. I was just curious.
Right. I might not be entirely consistent, but
yeah.
I guess so with Dominic Verity, a research colleague, we developed this notion of an infinity cosmos, and our plural there is infinity cosmoi. So I guess that's consistent with my whatever I said about toposes just now.
So what is an infinity
cosmos? Sure. So it's a what we're trying to do is develop the theory of infinity one categories, like the theory of one category. So by the theory of one categories, I mean, once you know what a category is, you want to know what limits and colimits are. You want to know what adjunctions between categories are. You want to be able to prove that right adjuncts preserve limits. That's sort of the theory of one categories. So infinity one categories are meant to be analogous to one category. So you ought to have the same definitions in that setting and the same theorems. And we certainly do. So, they've been developed by André Riehl, Jacob Lurie, many other people. But the traditional approach to infinity category theory required sort of a presentation of an infinity category, something we call a model of an infinity category. But the term model is a bit of a misnomer. And what I mean by that is it's difficult to define exactly what an infinity category is in the traditional set-based language of mathematics, just because an infinity category doesn't have a whole lot of sets in it inherently. So it's, if you're trying to define a mathematical object that is a set or a family of sets with a bunch of maps and structure, that's the language of set theory is excellent for that. It's just not so easy to define an infinity category. So these presentations are, I guess, they capture the idea of an infinity category in traditional foundations, but there's something a little bit inesthetic about them because they have to make a bunch of choices about, maybe the shapes of the data involved and the way the kind of weak composition is encoded that feel unnecessary. So what Dom and I have done is found a new approach to developing the theory of infinity categories that doesn't require a definition of infinity categories.
Interesting.
And that approach is sort of suggested by the philosophy of category theory. So if you so you can characterize an object in a category by its relationship to all the other objects in the category without necessarily knowing so much about that particular object itself. And so our strategy for proving theorems about infinity categories is to zoom out a level and think about the category in which infinity categories live as objects. And that's what we call an infinity cosmos. It's an axiomatization of the sort of category in which an infinity category is an object.
Okay.
And so we can prove a bunch of theorems about infinity cosmoi that specialize to all the different models or all the different presentations of infinity categories.
Cool.
Yeah.
Cool. And then is it because you sort of mentioned that because there's not a lot of set theoretic things going on when it comes to infinity categories, typically are you working in like different foundations or is that not even
It's a great question to ask. So this work that I was referring to now is in traditional foundations. So an infinity cosmos is ultimately a set-based structure. So we're sort of cutting the Gordian knot somewhere and sort of at that level. Otherwise it'd be sort of turtles all the way down.
Right.
But I am very interested in the potential of redeveloping infinity category theory and other sort of homotopy theoretic based mathematics in an alternate foundation system, something like homotopy type theory, maybe augmented in some way. So Mike Schulman and I have a paper that explores that approach. I've just written an expository article that's sort of a summary of these different approaches in traditional foundations and in proposed new foundations to infinity category theory, and sort of a dream for a future. This article is called Could We or Can We, I forget, teach infinity category theory to undergraduates? Because my personal point of view is if we're ever going to be able to streamline this theory to the, so that it could be part of the undergraduate curriculum, not certainly now, but maybe in 100 years time, it might be because we've swapped out our foundation system or sort of enriched our foundation system in this way.
That is something I think about a lot too, is the sort of chunking of levels of mathematics. As we get to a certain point where it seems like the edge of the field is so far out there, and it's gonna take someone 20 years to be able to start doing research. But then and I also think that this speaks to the value of those people who come along and clarify, which is exactly coming back to the point about definitions and categories. And I do imagine a future where in grade school somehow you're learning about categories or something.
Well, I don't know.
That's maybe a bit extreme. That's maybe a bit extreme, but yeah.
Anyway, it's exciting to see where mathematics is going.
Certainly. Well, I think that's a very perhaps inspiring and forward-thinking note to leave off on. Then I'll be sure to include some of the articles and content that we discussed in the link in the description. So thank you so much for joining me today.
Yeah, thanks. It was a real pleasure.
Yeah, thanks.
All right.
See you, everyone.